Now, there are always forces that cause a centripetal acceleration. And the very important thing to keep in mind, very important, is that objects can only have centripetal accelerations if there is some external force acting on the object. If there's not an external force acting on the object, you cannot have a centripetal acceleration. Okay, so there are a few examples of things that can constitute that can cause centripetal acceleration, motion around a circle. For example, you could have a ball whirling around in a circle at the end of a string. The force that's causing the centripetal acceleration is the tension force in the string. You have to have a tension force in the string in order for that object at the end of the string to be able to execute that circular path. You could have a car moving on a flat circular track, and the friction force between the car and the road is what causes this car to make a centripetal acceleration, or to make that turn, make circular motion. A satellite in circular orbit around the Earth, the force causing the centripetal acceleration is the gravitational force between the satellite and Earth. So you have to have a force to create the centripetal acceleration. So our centripetal force is equal to the mass of the object times the centripetal acceleration. So that's equal to the mass of the object times v squared over r. This is a way we can quantify centripetal acceleration. We could also say that the centripetal force is equal to mass times omega squared r, because that's another way we can quantify centripetal acceleration. When we apply Newton's second law to problems that have circular motion, then we see that it's the sum of all the forces in the radial direction. That's the sum of all the forces along the radius of that circular path. The sum of all those forces has to equal the centripetal force. That means that the sum of all those forces acting along the radius of the circular path must equal the mass times the centripetal acceleration in the problem. Okay, so in the homework, you're going to have a problem where maybe you have something spinning around on a string, okay? And then in that case, the centripetal force is the tension in the string, okay? That tension in the string has to equal the mass times centripetal acceleration of the object that's being swung around on that string, okay? Now also we're going to apply that idea of circular motion to solve a problem when a car goes around a curve.
When you go around a curve in your car, the thing that's keeping you from skidding out is the coefficient of static friction between your car tire and the road. That coefficient of static friction is the thing that is providing you with the centripetal acceleration to make the curve. Because there's a centripetal acceleration, we also have a centripetal force. And so here we're going to work through a problem where we're going to calculate this coefficient of static friction between car tire and a road when we go around a curve. Okay, so we have a race car that is traveling at a constant speed of 13.4 meters per second on a flat circular turn with a radius of 50 meters. So here's my car going around this turn. The radius of that turn is 50 meters. What minimum coefficient of static friction between the tires and the roadway will allow the car to make the circular turn without sliding? Okay, so again, the thing that is providing us with the centripetal acceleration to make this turn is the force of static friction acting on the car, okay? And so before we even get going on this problem, I've drawn a picture of what we look like from above. Let's draw a free body diagram of the car. So here we've got the surface of the road. There's no incline. We've got our car. And for a free body diagram, we've got the normal force upward. Okay, that's the force that the road is pushing up on the car with. And then we have the weight of the car downward. That's its mass times gravity. Okay? We also have the friction force. So I'm going to draw the friction force pointing in this direction here. Okay. So the friction force, this static friction force, is always going to be pointing inward toward the center of our curve. Okay. That's the static force that is keeping us from sliding out of the curve. Okay. And so this static force is providing us with the acceleration, the centripetal acceleration to go around the curve. Okay, so the force of static friction is always going to be pointing wherever the car is inward toward the center of the curve. Okay, that's also the same direction that the centripetal force is pointing toward the center of the curve. That also means that that's the same direction in which our centripetal acceleration is pointing toward the center of the curve. So in order to solve what is this coefficient of static friction, we are going to use still Newton's second law, but thinking about all the forces acting in the radial direction. And so for us, that means all of the forces that are acting inward toward the center of the circle. So we have the sum of all the forces in the radial direction, radial along the radius of the circle, equals the mass times acceleration, but this time it's the centripetal acceleration. And again, it is this static friction force that is giving us this centripetal acceleration. Without the static friction force, we wouldn't have this circular motion. Okay, so the only force we have acting in the radial direction is our static friction force. The static friction is providing us with our centripetal force. Static friction force equals the mass times the centripetal acceleration. Now we know we can also write the centripetal acceleration as v squared over the radius of our turn, or the radius of our circle here, the curve around which we're going. Okay, we wanted to use our velocity in here because the only givens we were provided with in the problem is the speed around which we're moving around the circle and the radius of the circle. So we want to use these terms here. The problem is asking us for this coefficient of static friction, the minimum coefficient of static friction in order to keep us going around the circular path. So our minimum static friction force is going to be equal to our coefficient of static friction times the normal force, and that equals mass times the velocity squared over r. Okay, so what's the normal force? Here we're on a flat surface, we're not on an incline, so the normal force is just equal to the mass times gravity. And you can always prove that to yourself when you're on a flat surface. These are our forces in the y direction, so if you do Newton's second law in the y direction, we're not accelerating in the y direction, so the sum of all the forces in the y direction has to equal mass times acceleration in the y. We're not accelerating in the y, so that's 0. Okay, so then we'll have the normal force minus the weight equals 0. So then this just tells us that the normal force must be equal to the mass times gravity. So you can always prove that to yourself. So for the normal force, we can plug in our mass times gravity, and then we'll have the coefficient of static friction times mg equals mv squared over r. Okay, we see that the masses cancel out on both sides of the equation. We didn't even need to know the mass of the car. That's another good reason why we should always solve equations algebraically, because sometimes I won't provide you with some of the quantities because some of them are going to cancel out if you actually solve the problem algebraically like this. Okay, so we're looking for a coefficient of static friction. We divide both sides by g. So the coefficient of static friction is equal to our velocity squared over the acceleration due to gravity times the radius of our curve. Okay, so then that equals 13.4 meters per second squared divided by 9.8 meters per second squared times the radius of our curve, which is 50 meters. And then that all equals 0.5 0.367. So we need at least a coefficient of static friction of 0.367 between the car tire and the road in order for us to execute this circular curve without sliding out.
We can also apply circular motion in order to understand artificial gravity. If you're a sci-fi fan, then you have probably seen this in action in many a science fiction TV show or a film. So usually on a flat surface, we know that our normal force is equal to the mass times gravity. That's the force that the surface we're standing on is pushing back up on us with. That's what gives us our feeling of weight. But what about in space, when you're far enough from any planetary body that you are literally weightless? So you're way out in deep space. What gives you that gravity that allows you to walk around inside the spaceship? Well, we can artificially create an acceleration to mimic the acceleration due to gravity on Earth by spinning a spacecraft fast enough that the centripetal force supplied by the floor would be enough to replace your usual normal force that we feel on the Earth. So we could use this idea to solve this problem here. At what angular velocity would we need to spin a cylindrical spacecraft like this of radius 150 meters if we are trying to mimic the acceleration due to gravity on Earth? So acceleration due to gravity on Earth is at 9.8 meters per second squared. Okay, what do we need to do? We need to apply our Newton's second law in the radial direction and think about this idea that we can mimic gravity on Earth if we find a situation where we can match the normal force that we would feel on the surface of the spacecraft with the centripetal force that we would feel because we're executing circular motion. Okay, so we've got our cylindrical spacecraft here. It's my best attempt, okay? And it has a radius of 150 meters. Okay, and we are trying to spin it fast enough so that we could literally stand on the edge of the spacecraft as it's spinning around. And in that situation, our centripetal force would be replacing our normal force that we would usually feel. Okay, so imagine that I'm standing on the edge of this spacecraft here. Then my normal force would be pointing toward the center of motion, or would be pointing toward the center of the cross section here of our cylindrically rotating spacecraft if we're rotating sort of around in this direction. Okay, that would be our angular speed, the speed at which the cylinder is rotating around the central axis. So normally, our normal force is equal to our weight, our mass times gravity. All right, so in order to get us a normal force, we have to spin the spacecraft really fast. Okay, so the sum of all the forces in the radial direction, we know, has to equal the mass times the centripetal acceleration. So the force in the radial direction would just be this normal force that we experience from the edge of the spacecraft, okay? And in order to mimic the normal force that we would experience on Earth, this needs to match our mass times gravity, okay? And then that has to equal the mass times the centripetal acceleration, our mass. Now remember, we can write our centripetal acceleration as v squared over r, or omega squared times r. So in this situation, it makes sense to use the second formulation because we're looking for what angular speed do we need to spin up the spacecraft so that we can mimic the acceleration due to, so that we can mimic gravity here on Earth, okay? So we can replace the centripetal acceleration with omega squared r, okay? And that has to equal our mass times gravity. In this case, I'm gonna say gravity artificial because it's not Earth's gravity, but it's trying to match. We're trying to spin the spacecraft fast enough that we can match the acceleration due to gravity on Earth. And we see in this equation that on both sides, the masses cancel. So what I'm calling artificial gravity equals our angular speed squared times the radius. So let's see, angular speed squared is equal to our artificial gravity divided by the radius of our spacecraft. So square root both sides. Then the angular speed that we need to mimic Earth's gravity, or our acceleration due to gravity here on Earth, is equal to this artificial gravity that we can achieve divided by the radius of our spacecraft. Doesn't matter, big R, little r, whatever, it's still the radius of the spacecraft here. So in this case, we're trying to mimic the acceleration due to gravity on Earth. So where it says G artificial, we're gonna go ahead and put in 9.8 meters per second squared. But if I were asking you what angular speed do we need to mimic the acceleration due to gravity on Mars, you would need to put, for G artificial in this equation, you would need to put the acceleration due to gravity on Mars. And then we need to divide it by the radius of our spacecraft, which was 150 meters, okay? And so then we find that the angular speed we need is 0.26 radians per second. That's how fast this spacecraft needs to be spinning, the cylindrical spacecraft, in order for us to mimic the acceleration due to gravity on Earth. And if you pay really close attention to some of these sci-fi movies where you've got, where you have astronauts or people in the spaceship that are walking around in deep space, the only way they can do that is if somehow that spacecraft is spinning enough around a central axis in order to create this artificial gravity, just like the problem that we've described here.